All right, let's talk about electromagnetic radiation. The word electromagnetic is often shortened to EM. These are waves of energy that are capable of passing through a vacuum and sometimes other media like solids, liquids, or gases. Some of the waves are long and some of the waves are really incredibly short. That means in order to describe the waves, we often talk about their wavelength. Wavelength literally means the length of one wave, and we always measure it in meters. Now, sometimes if it gets really, really small, we'll convert that into millimeters or micrometers, or even smaller still would be nanometers. But the thing that those things have in common is that they're all basically measures of the meter. They're just fractions of the meter. We can also talk about a wave's frequency, and this means how many waves pass a particular point in 1 second. This is measured in hertz, which is given the symbol capital H, lowercase z. 1 hertz is equal to 1 wave per second. Therefore, 12 hertz would be equal to 12 waves per second. Now, if you think about that for a minute, think about those two things. If a wave gets really, really long, it won't come very often. So that means as wavelength goes up, frequency will go down. The opposite is also true. If a wave is really, really short, it will come very frequently. It will come very, very often. And so what that means is that as wavelength decreases, frequency increases. So the two are the inverse of each other. If one gets big, the other gets small. We can also talk about waves in terms of their energy. That's how much energy the wave is carrying. And like other measures of energy, it will be measured in joules, or parts of joules. And joules are measured with a capital J. Now let's think about the relationship between these three things, all three of them. If a wave is really short, it will come very often, so it will be very frequent. But it will also be quite high energy. So a wave that is short and frequent will bring more energy than a wave that is long and infrequent. So think about if you were bobbing on a water wave on a surfboard. If the wave was short, it would come very often and it would feel very energetic. But if the wave was long, it would come not very often, and it wouldn't feel so energetic at all, so you wouldn't have to struggle so much to stay on your surfboard. Now, light is a form of energy, right? It's a wave of energy. And if light passes through a prism, a rainbow appears. The prism is scattering the light into all of the waves of energy that the white light is made of. This means that visible light is a mixture of different energy waves that our eyes detect as red, orange, yellow, blue, green, or violet. The energy waves that we can see, the visible light, are only a very small part of all of the waves of electromagnetic energy, EM energy, that exists. The range of EM energy is called the electromagnetic spectrum, or the EM spectrum. Here's a diagram illustrating the spectrum, the EM spectrum. As you can see, visible light is only a very, very small part of all of those waves of energy that actually exist. These just happen to be the parts of the lengths of wave that our eyes are capable of detecting. If you have a really careful look at that visible spectrum on the screen, you'll see that the red light has wavelengths of up to 750 somethings. In fact, that's nanometers, but it has a wavelength of 750. Meanwhile, the green light has wavelengths of a maximum of about 570. So that means that waves of red light are longer than waves of green light. And as we discussed a minute ago, that will make them less energetic. The most energetic form of visible light is the violet light, and that will be as short as 380 nanometers. 380 is good enough. So that means that those that beyond that, the waves are too short for our eyes to be able to see. So there's all these different types of wave energy out there. Just because we can't see them, they look black, doesn't mean they aren't there, and doesn't mean that we can't detect them in other ways. Before we move off of this diagram, can you also notice, please, that once again, if wavelength increases, if the length of the wave gets longer, the frequency will decrease. So the two are increasing in opposite directions. Wavelength is increasing toward the right, and frequency is increasing toward the left. All right, waves that are a little bit too long for us to see are called IR. That's short for infrared. Our bodies can detect infrared radiation as heat. A little bit longer than that is microwave radiation. Those waves are a little bit longer than the infrared waves. Now, we don't detect, as humans, we don't detect microwave radiation very easily, but we can certainly make it work for us. Your microwave oven is called that for a reason. When you turn on the microwave, it starts to emit microwave radiation into the cavity that you would call the stove or the oven. Those microwaves are picked up by water molecules in your food. When those water molecules are hit with microwaves, they go bananas and they start to vibrate really, really quickly. And this heats your food up. Now beyond that, so much longer than red visible waves, is the radio waves. Again, we can't really detect them, but we have constructed detectors that can detect radio waves, and that's how you listen to the radio. On the other hand, though, waves that are too short for us to see, there are three different types. The first is called UV. So these are a little bit too short for our eyes to detect. We can't see ultraviolet radiation. That's what UV stands for. But we can certainly feel it when it coming from the sun, when it burns our skin. A little bit of UV radiation is helpful for us when it shines on our skin. It helps us to make vitamin D. It also helps to drive photosynthesis in plants. But too much of a good thing is definitely a bad thing. And the damage that's caused by ultraviolet radiation can cause changes in our skin that lead to cancer. Even shorter, that means even more energetic than ultraviolet waves, are the X-rays. Again, we can't really detect the X-rays particularly well, but we use them by aiming an X-ray source at our bodies if we want to have a look inside, particularly at the harder structures that our bodies are made out of, like bones. So you would have had an X-ray if a doctor ever wondered whether you'd broken a bone. even shorter than that, the shortest of all are the gamma rays, and that's what that funny little symbol that kind of looks like a Y stands for. That's the Greek letter gamma. Gamma rays are incredibly short and therefore incredibly high energy. We use gamma rays very, very cautiously when we're trying to detect changes in our bodies that might indicate cancer, when we're trying to indicate changes in our body that might indicate something's not working so well. Now, this is for soft tissues, not bones. We also use gamma rays when we want to kill cancer cells. Gamma rays are incredibly energetic, and they can absolutely kill living things. So once again, I want to make this point that as wavelength decreases, frequency increases, and so does energy. So the shortest, most frequent waves are the most energetic ones.